that where we measure distance in terms of the number of edges in a path, right? Today, we're going to generalize that notion, but I just want to go over what we've talked about in the last two lectures. In the last two lectures, we've talked about two algorithms, breadth-first search and depth-first search, to solve a range of problems. Here's some of the problems that we've been solving. Single source shortest paths, where distances are measured in number of edges in a path. And we use BFS to solve this problem, starting from a single source, usually a vertex S that we call. And we solved that in linear time, right? We solved that in order V plus E. That's what we called linear time for a graph. For the special case of single source reachability, here we had to return a shortest path distance for every vertex. And there was at most E things reachable from a vertex. So this is the bound we got. But in the special case for single source reachability, when our output only has to list the vertices that are reachable from me, the number of things reachable in basically a spanning tree of the connected component of my source can almost be of order E. And so for all the little singleton vertices in my graph, I don't really E. And so for all the little singleton vertices almost be of order E. And so for all the little singleton vertices in my graph, I don't really care, right? So I can get this in order E, but that's kind of a little optimization. The next thing we did was we talked about connected components. And we didn't just reduce to using a search algorithm like a single source reachability algorithm like BFS or DFS. We put a for loop around that to explore the entire graph by basically saying if I've explored one connected component, then I can look at any other vertex I haven't seen and explore the next one, right? And so that actually, with a little analysis, also got linear time because I'm at most traversing any component of my graph once. That's kind of the idea. And then, and we can use that using BFS or DFS, really, because we're just trying to get a thing that searches an entire connected component. And then this topological sort we did at the end of the last lecture. We used full DFS to give an ordering of the vertices in a DAG. Maybe I'll specify clearly that this is only for a DAG, right? Where we have an ordering of the vertices so all the edges go forward in that order, for example. Okay? And that we also did in linear time. All right, in this lecture and in actually the next 4 lectures, what we're going to do is, instead of measuring distance in terms of the number of edges in a path, so previously distance equaled number of edges, we're going to generalize that notion. So instead of counting an edges, we're going to generalize that notion. So instead of counting an edge, we're going to count an integer associated with that edge. It's going to be called a weight, all right? So here's an example of a weighted graph G, and I've labeled in red weights for each of these edges. There's a directed graph on 8 vertices, and I've got an integer associated with each edge. You'll notice some of them are positive, some of them are negative. It's okay to be 0 as well. It's just any integer edge weight here. So generally, we're going to be, along with our graph G, we're going to be given a weight function